Hey guys, welcome back to Math from My Desk. Today I'll be answering question 3 from the AP Calculus AB and BC 2024 FRQ. So let's go ahead and start. So the depth of seawater at a location can be modeled by the function h that satisfies this differential equation over here, where h of t is measured in feet and t is measured in hours after noon, where noon is t equals 0, and it is known that h of 0 equals 4. So a portion of the slope field for the differential equation is provided. We want to sketch the solution curve y equals h of t through the point 0, 4. So let's go ahead and do that. So this is just following the slope field over here. So we start here. We're going to go something like this, I would say. I'd say this would be an acceptable answer, and I feel pretty confident about this. So let's go ahead and move on. So for 0 is less than t is less than 5, it can be shown that h of t is greater than 1. We want to find the value of t for 0 is less than t is less than 5, at which h has a critical point, and we want to determine whether the critical point corresponds to a relative minimum, a relative maximum, or neither a relative minimum nor a relative maximum of the depth of seawater at the location, and we want to be able to justify our answer. So first, we know, the way I would approach this is, we know to find a critical point, we need the derivative to be equal to 0. So we set the h dt is equal to 0. And since these terms are not in terms of time, I'll only care right now about cosine of t over 2. I'm going to go ahead and set that equal to 0. And immediately, I'm thinking the values in which cosine is 0 are pi over 2 and 3 pi over 2, and this should equal t over 2. So we multiply by 2. That gets rid of the 2's, and we're left with pi and 3 pi. However, an interval is from 0 to 5, so we can get rid of the 3 pi. So I'm just going to go ahead and delete all that to make space. So our critical point is going to be pi. So I can write that as critical point, and that is our only critical point. So now we want to know if that is a relative minimum, a relative maximum, or neither. So the way I would do that is looking at the first derivative. So we can set a number line, and we're going from 0 to 5, right? And pi is going to be somewhere a little over here. And we want to see if over here is going to be positive or negative, and over here positive or negative. So I can pick test points. So a test point, for example, here would maybe be 3 pi over 2, right? And then over here, let's say pi over 4. And okay, let's see. That should be positive, because cosine of pi over 4 is definitely positive, right? Square root of 2 over 2. And this should be negative, because if we think of it as our unit circle, it's going to be in this quadrant over here. So we're talking about negative x, and we know the unit circle that cosine is x, so this would be negative. So since we're going up and then we're going down, we're talking about a relative maximum. So I would say this would be my approach. I'm not sure if this is the correct way though. So let's move on now. So use separation of variables to find y equals h of t, the particular solution to this differential equation that we have over here, with an initial condition h of naught is equal to 4. So, okay, this is simply solving a differential equation. So first we're going to have dh and over h minus 1. All I did here is I divided h minus 1 by both sides, and now I'm moving dt to this side. So I have 1/2 cosine of t over 2 dt. And then I integrate. Actually, for that one, let me just, the 1/2 is a constant term, so I can keep that up. So we have cosine of t over 2, and you can do the u substitution in your head for that, but to replace, to like sort of make up for it, we'd need to bring a 2 over here. So 2 times 1 over 2 would just cancel out and it end up being 1. So here we have the natural log of h minus 1. However, we know we're given that h is always greater than 1. We were given that somewhere previously in the problem, so we don't need to have the absolute value with the natural log of h minus 1, simply the natural log, the natural log of the absolute value of h minus 1, simply the natural log of h minus 1. So we have the natural log of h minus 1 is equal to sine of t over 2 plus c. Then we're going to have e in our base. And let me move here for my work. So now we have h minus 1 is equal to c e to the sine of t over 2. Now if we want to figure out the constant term here, we're gonna, let's see, we're given initial condition h not equals 4. And let me add 1 to both sides here. Okay, so we're gonna have h, so 4 is equal to c times e to the sine of t over 2, where t is 0, so sine is 0, it's just 0, e to the 0 is 1, c plus 1, minus 1 minus 1, c is equal to 3. So now if I want to write the general solution to my differential equation, let me just make some space. We're left with h is equal to 3 e to the sine of t over 2 plus 1. And this, I would say, is the solution, the particular solution to this differential equation. I hope you guys enjoyed this video.